Before watching this video, please subscribe this channel and click on bell icon to get the notifications for the upcoming classes.
Welcome to Thermodynamic classes. In this class, I want to explain you some worked out examples in thermodynamic processes in gases. So the first example is 2 kg of air at 10 bar and 327 degrees C expanded adiabatically to a pressure of 1 bar. Determine the final volume, final temperature, work energy transfer during the process, change in internal energy and change in enthalpy. For the Cp 1.05, R is equal to 0.287. So this is the previous question paper. This problem is coming from the previous question paper. So here, so it is clearly mentioned that adiabatic process, adiabatically expanded adiabatically. So what is the adiabatic process? So adiabatic process is represented with PV to the power of gamma is equal to constant. So in the adiabatic process, all of you should remember the relations. So that is P1 by P2 is equal to V2 by V1. Reversely, that is to the power of gamma. This side T1 by T2. Just remember this gamma by gamma minus 1. So everyone should remember this relation for adiabatic process and polytrophic process. This is the important relation for any any problems related to the adiabatic and polytrophic processes. So next, okay, then now I enter to the problem. The data given is m is equal to mass is equal to 2 kg, pressure P1 is equal to 10 bar. So that is converted into 10 into 10 square kilonewtons per meter square. So next temperature, that is 327 plus 273, that is 600 Kelvin. Next to a pressure of 1 bar, as the pressure is expanded 1 bar. 1 bar is equal to 1 into 10 square, that is 100 kilonewtons per meter square. This is the data. Now remaining data is Cp and R is also given. So what? So determine the final volume. So we should plan for the final volume, final temperature. So as the P1 and P1 and P2 given here. So there is a relation P1, P2, but V2, okay, here V2 by V1. Okay, first of all, V2 by V1. Here, this is the relation P1 by P2. Here the P1 and P2 is given. So V2 and once V1 is determined, it is very easy to get the V2. So that is the general equation for PV is equal to P1 V1 is equal to MR T1. Okay, so that is P1 is mass 2 kgs, R is given here, R is given here, T1. So T1 is given here. Once V1 is calculated, as P1 is given, M is given, R is given, T1. Once V1 is calculated, you put this V1 here and you can get V2. Then the final volume is next final temperature. So final temperature the same way. So P1 is given, P2 is given. So gamma, what about the gamma? Gamma for adiabatic process, that is gamma is equal to 1.4. Otherwise you can also calculate gamma is equal to Cp by Cv, or gamma is equal to Cp by Cv. So Cp and Cv values you can obtain by Cp and R value, that is Cp minus Cp minus Cv is equal to R. So gamma is equal to Cp by Cv. So you can calculate the Cv value, that is Cv is equal to Cp minus Cv is equal to R. Cp minus Cv is equal to R. You can calculate the R value. Okay, so gamma value. So gamma value, so as it is adiabatic process, this is 1.4. Okay, so now I am going to, okay, next, first of all you should plan for the, okay, first one is the final volume. So we can calculate here. So final temperature, the work energy. What is the work energy? That is work energy P1 V1 minus P2 V2 by gamma minus 1. That is okay. Next, change in internal energy. Okay, everything okay. So here, that is first one is final volume. Second one is final temperature. So third one is work done. Fourth one is change in internal energy. Fifth one is change in, that is enthalpy. So both of these we can determine this, we can calculate this by using the relations. So W is equal to formula P1 V1 minus P2 V2 by gamma minus 1. So in adiabatic process for NFEE equation, that is Q is equal to W plus delta U. Here, as the adiabatic process, in adiabatic process heat transfer is 0, that is W is equal to minus delta U. So once you calculate W, so internal energy is the minus W. So what about the enthalpy? What is the enthalpy? Enthalpy you can also calculate as a mcp T2 minus T1. So everything is a mcp T1. So this is the plan. Now we are going to the solution. Okay, so first one, final volume. So final volume P1 V1 is equal to MR T1. So P1 V1 is equal to MR T1. So that is V1 is equal to MR T1 by P1. So M is equal to 2, R is equal to 0.287 as it is given, into, so T1 is equal to 600 by P1 is equal to 1000. Okay, here, so here this is a 10 into 10 square, this data is used. Okay, 10 into 10 square, that is 1000. Okay, okay, 1000. Then you can calculate V1 as V1 is equal to 0.344. Okay, so for the adiabatic process, okay, a 4 meter cube. Okay, adiabatic process, there is a relation, that is, now you can calculate V2 by V1 is equal to P1 by, already I explained, P1 by P2 is equal to, okay, there is a relation, this is the relation. So you can also use this, P1 by P2 is equal to V2 by V1. Okay, so by using this relation, you can calculate the V2. So in this relation, so you should transfer this gamma to this side in order to free up this terms. So just you transfer this gamma to this side, then it becomes as, so V2 by V1 to the power of gamma that is P1 by P2. So 1 by gamma becomes as 1 by gamma when you transfer from this side to this side, that is V2 by V1 is equal to P1 by P2 1 by gamma. Then V2 is equal to V1 into P1 by P2 to the power of 1 by gamma, that is V1 is equal to 0.344, that is P1000 by 100 to the power of 1 by 4. Then V1 is equal to V2 is equal to 1784 meter cube. So next, second one, B, that is final temperature. So you can use this, you can calculate this also with the relations between that is P1 by P2 is equal to V2 by V1 to the power of gamma, or T1 by T2 whole to the power of gamma by gamma minus 1. Can use any of the relation. So any of the P1 by P2 is known, or V2 by V1. So V1 is already known, V2 already. So any one of these relation you can use it to find the T2. So I want to use this relation. Okay. So this relation, that is V2 by V1 to the power of gamma is equal to T1 by T2 to the power of gamma by gamma minus 1. Gamma, so gamma is cancelled. Then T1 by T2 is equal to V2 by, so V1. Once this 1 by gamma, so as the here 1 is there, 1 by gamma is transferred to this, so this side, then it becomes as a to the power of gamma minus 1. Here 1 by gamma, so whenever this is transferred to this side, so this become as a 1 by gamma, that is by gamma. So there is no value for by 1. Then T1 by T2 is equal to, so V2 by V1 to the power of gamma minus 1. Then you can write this as, so V2 is equal to 1.784 by V1 is equal to 0.344 to the power of 1.4 minus 1, that is 5.18 to the power of 0.4. So that is 1.93. So 1.93, that is T1 by T2 is equal to 1.93. Then T2 is equal to, so T2 is equal to T1 by 1.93, that is T1 is equal to, so 600 by 1.93 is equal to, so 310 degrees K, that is minus 273 is equal to 37 degrees C. So both 1 and 2 is simply calculated with the help of the relations between the general relations between the, so pressure, volume and temperature. These relations are very very important during the for the solving the problems for adiabatic and polytropic process. So next, so third bit is work done. So work done, that is P1 V1 minus P2 V2 by gamma minus 1. So P1 is there, P1 V1 everything is here, that is 1000 into V1.344 minus 100 into 1.784 by gamma is equal to 1.4 minus 1 is equal to, so 415 kilojoules. So third bit, this is the straight one. So everything is available. So some of the data is directly given. So some are we are determined, that is V2. So next one, fourth bit, that is internal energy. Okay, internal energy. So internal energy. So NFEE equation, according to the NFEE equation, so Q is equal to W plus delta E. From the first law of thermodynamics, it is derived that So as it is the adiabatic process, so neither heat transferred to the system nor rejected from the system, that is Q is equal to 0. So Q is equal to 0, that is, so 0 is equal to W plus delta U. Then so delta U is equal to minus of W, that is minus of W here 415 kilojoules. Okay, so negative sign indicates, so internal energy is, so internal energy decreased. Okay, internal energy decreased. Okay, next, fifth bit. So fifth bit, that is E. So E is equal to, so change in enthalpy. So change in enthalpy, delta H is equal to, this is the basic formula, mCp T2 minus T1, that is m is equal to 2 into Cp is equal to 0.05 into, so 310 minus 600 is equal to minus 580.2 kilojoules. So here also negative sign, it indicates the, so decrease in enthalpy during this process. So in this way you can solve any problem by using this relations and with the concept of adiabatic process. Now the second problem. An ideal gas initially at a temperature of 250 degrees C and pressure of 10 bar expands adiabatically to a pressure of 2.5 bar. Calculate the final temperature if the adiabatic index for gas is 1.4. So this problem is also from the previous question paper. So here everything is so here ideal gas initial temperature T1 is equal to 250 degrees C plus 273. So next, so 273, that is 523. So next one is, so pressure P1 is equal to 10 bar, that is 10 into 10 square, that is 1000 kilonewtons per meter square. So to a pressure of P2 2.4 bar, that is 2.4 into 10 square kilonewtons per meter square. So they ask to find the final temperature. So calculate the final temperature, that is, so what is T2? Very simple problem. We can simply solve this problem by using the relations between the pressure and temperature in adiabatic process, that is PV to the power of gamma is equal to constant pressure process. In this process the relations between, so everyone tries to remember this equation in this form, that is P1 by P2 is equal to this side V2, reverse side V2 by V1 whole to the power of gamma. So this side P1 T1 by T2, remember this gamma by gamma minus 1. So here everything is okay. So P1 is given, so P2 is given, okay, P1 by P2. So P1 is given, P2 is given, so T1 is given. So everything is given. Just simply you can put the values, that is P1 to 1000, P2 2400, so T1 250 260 degrees to 523 degrees. Just I go to solve this problem just. So T1 by here P1 by P2 is equal to the part of the relation, that is T1 by T2 whole to the power of gamma by gamma minus 1. So as it is required to find the T2, then this part, this exponent part is transferred to this side, then it becomes as T1 by T2 is equal to P1 by P2 whole to the power of gamma minus 1 by gamma. Then you can calculate P1 is equal to 1000 by 2400, as it is given as a 10 bar and 2.4 bar. I think 240 only, that is 2.4 bar. 2.4 into 10 square, 2.4 into 10 square 100, that is 240. So 10 into 100 is 1000. Okay, so then, so here 1.4 minus 1 by 1.4, so then it is 4.167 whole to the power of 0.2857 is equal to 1.503. So that is T1 by T2. So don't try to solve at a time. Okay, so first of all you solve this equation by putting the numericals by step. Okay, so T1 by T2 is equal to, so 1.503, then so T1 is equal to 1.503 into, so T2, then T2 is equal to T1 by 1.503, that is T1 is equal to 523 by 1.503, that is 347 degrees Kelvin. So if you want the answer in degrees Kelvin, you just divide, you just subtract with 273 degrees Kelvin in order to obtain the, that is 347 minus 273 is equal to 74.97 degrees C. So these are the problems about the regarding the adiabatic process. So in this process, very important relations are, so for to solve any problems, you should remember these relations. That is, this is the relation. You try to remember this equation in this pattern. P1 by P2 is equal to T1 by T2 gamma by gamma minus 1 V2 by V1 to the power of gamma. At the same time, so NFE equation, but the first law of thermodynamics, whenever it applied to the adiabatic process, that is heat transfer to the system is 0. That is W is equal to Q is equal to W plus delta U, that is delta U is equal to minus W. Okay, thank you.
Thank you for watching this video. Please subscribe this channel and click on bell icon to get the notifications for the upcoming classes. And share this